So let's go ahead and prove the law of cosines. And just like we did with the law of sines proof, we're going to sketch a triangle. We'll be very clear about it not needing to be any particular kind of triangle. Okay. So it could be scalene, it could be right, could be obtuse as we see here. Try to make that look obtuse. And we'll go ahead and label it as follows. So A, B, and C. And then, of course, as is probably expected, the lowercase letters opposing their respective angles of the same letter. Okay, so the claim, okay, it's actually one claim, but it's generally provided in 3 statements, but we'll see that each of these statements is equivalent. Starts to look like the Pythagorean theorem, but then it starts to change direction. And so you have this statement, you've got this statement, and then of course you've got this statement. Now, again, these labels are entirely arbitrary. This doesn't have to be B and capital A and little a opposing it. This could be capital B and little b opposing it, for example. So to prove one of these is the same as proving any of them. And that, I suppose, from the outset should be established. So I'm not going to try to prove all 3 of these. That would be redundant. Again, these variables are entirely arbitrary. It just depends on how you label them. But we know we will have this 3-way relationship. Okay, and so there you go. Okay, let's try to prove this. And I am going to use the diagram. Okay, I'm going to use the diagram here. So let's get a height in there. I think that's step 1. We'll call that H. And let's call this here T1, and let's call this here T2. Okay. So I can think, so if I take the cosine of C, angle C, that's the same thing as T over B. T1 over B, I should say, excuse me. Okay, and so therefore I can think of T1 as B times cosine of big C. Okay, now I can also think of the sine of big C as H over B. And of course that is the same as H is equal to B, little b times the sine of big C. Okay, now we know that T1 plus T2 is equal to A. Okay, and so that means that T2 is going to be equal to A minus T1. Okay, we know also that T2 squared plus H squared must equal C squared. So that means that A minus T1 all squared plus B sine big C all squared equals little c squared. We don't want T1, so let's swap that out with what we know it's equal to, B cosine big C. So we're going to have A minus B cosine big C, all, of course, still squared, plus B squared sine squared C. Okay. Notice here I'm just using the property that if you have x times y and you raise it to the c power, both of those factors in the product are applied the power. Okay, that's a very important property of exponents, so let's put a box around that. And then, of course, that's all equal to c squared there. Okay. Okay, we've got everything we want. We don't have the t values, and we didn't want those. We got the little a, little b, little c, capital C. So we're going to hopefully get this bottom statement here. Okay, in fact we are. I can already see it coming together quite nicely for us. So we have a squared minus 2ab cosine big C plus b squared cosine squared C plus b squared sine squared C is equal to C squared. And so we have a squared minus 2ab cosine big C plus b squared, and then I'm going to factor this out. So we have cosine squared big C plus sine squared big C is equal to C squared. Well, we would hope that cosine squared C plus sine squared C is equal to 1, because if that's the case, then we've proven the law of cosines. And some of you, most of you, I'm sure, know that this is equal to 1. Okay, but really quickly off to the side, let's not assume that we should know anything. Okay, let's again, on this channel, I want to be very diligent so as to never assume. Let's zoom out just a bit. Okay, so let's go ahead and establish what it would maybe mean to think about the cosine squared of C plus the sine squared of C equaling 1. Let's see if we can do this with just kind of a polar configuration. If you haven't seen any work on using polar coordinates, you can check out my video on that by doing a search on my page. Okay, so let's say this is theta, rather C, some angle here. Well, let's just call it, well, why don't we call it theta? That's typically what it's called. All right, and we're going to call this x comma y. We'll call this here r. So this here obviously is x, and this here obviously is y. And it's therefore obviously the case that x squared plus y squared equals r squared. But we also know that the sine of theta is equal to y over r, and the cosine of theta is equal to x over r. So that means that y is equal to r sine theta, and it also means that x is equal to r cosine theta. So now plugging in, okay, I'll throw an arrow down here, we're going to have r cosine theta all squared, because that's x being squared, plus r sine theta all squared, again, plugging it in here, equals r squared. Well, clearly this is r squared cosine squared theta plus r squared sine squared theta equals r squared. I can divide both sides by r squared, assuming r is never 0. It's in the quadrant. It's out here in the plane, in the first quadrant, so it isn't 0. There is some length. There's some magnitude here. This is called the magnitude. Okay, this here is called the argument. Sometimes we call this here the modulus, but typically when we're dealing with complex numbers we do, so I think for now we can just refer to it as the magnitude here. Okay, so the magnitude I can divide squared, I can divide out, and that is of course going to give me what I was looking to demonstrate, that if you square the cosine of an angle and you add that to the square of the sine of the same angle, it's going to equal 1. So this whole thing is 1, and therefore we have a squared minus 2ab cosine C plus b squared equals c squared, and we are done. That has demonstrated the proof, this statement right here. I hope you liked the video. Definitely let me know if you have any recommendations for future videos I could make. I am more than happy to spend time making such videos because I love mathematics. I always have, always will. And yes, again, we're going to prove every statement in mathematics at some point. It might take a few years to do it, but we're going to do it one video at a time and one proof at a time. Until next time, so long.